Digital futures is an important and emerging area of research at the University of Manchester and industry. A digital twin models the key aspects of the physical system to allow for condition monitoring, visualization, and to perform interventions when required. Digital twins was first introduced by NASA in 1970 to simulate conditions on the Apollo 13 vehicle. Digital twin technology can be used in various industries such as manufacturing, automotive, construction, utilities, and healthcare. The key motivating factor for this project was to support the needs of SMEs who may not have the capital or expertise for the latest advancements in digital twin technology. The machine under consideration is an induction motor. The aim of this project was to demonstrate how industrial IoT can be used for predictive maintenance and virtual teaching through the use of a digital twin. The diagram highlights the key components of the digital twin and how they connect to each other. Data was collected from the sensors in the motor drive unit and was preprocessed and packaged by the data acquisition system before being sent to the database hosted in the Amazon Web Services server. Data was then collected and processed by the data-driven models. The front-end software retrieved the processed information from the back-end and displayed the required information on the website.
The data acquisition system is responsible for collecting data from the induction motor. This is done by designing a custom program to run in the lab desktop and generating a communication link with the motor drive. The communication link is established with a CT USB comms cable that converts USB protocols to RS-485. The link communicates using the Modbus RTU protocol, capable of collecting values like root mean square voltage and currents. Finally, the collected data will be processed and sent to the database with a latency of less than 30 milliseconds.
The physics-based model was used to simulate the BRB fault in the induction motor and provide fault data to the data-driven model to train for fault detection. In this project, we used a Simulink software to model the BRB fault. The fault was modeled by adding an external resistance to the rotor of the induction motor. When comparing the FFT result of the model to the theoretical value, the obtained result has a percentage error of lower than 4%.
In order for the digital twin to accurately model the physical induction motor, machine learning algorithms using classification and regression were developed. MATLAB tools studied the dataset we had gathered from both the physical motor and Simulink model and calculated which algorithm produced the best validation score during training. Overall, 5 models were created. One classification model which predicts which operating state the motor is in and if the broken rotor bar fault is present, and 4 regression models which predict rotation speed and output torque, with 2 having the functionality to retrain, whilst the other 2 did not as they were used for virtual learning. By collecting over 3,000 training observations, the team produced a classification model with 99.6% accuracy, a speed regression model with a root mean square error of 3.5 revolutions per minute, and a torque regression model with a root mean square error of 0.5 Newton meters.
The backend program was fundamental to link different components together into a cohesive system. The backend program permitted real-time data generation by transferring data from the physical model to the MATLAB models, and transporting the model's output to a front end. And it handled HTTP requests from the web application on the front end. And APIs have been designed to provide corresponding data resources. The backend program was written in Java and designed based on the framework of Spring Boot, which can save developers time on configuring the environment. MySQL is used as a database and AWS is used as a cloud server.
The web page takes the user to the web application that monitors the motor drive unit and previews the data provided by the digital twin model developed in MATLAB. The web application consists of 3 applications: a monitoring application that visualizes data received from the motor, a data log application that lists the motor data, and the control application that is used to input data into the MATLAB digital twin and observe the output of the 3 different models developed.
Digital Twin PAL, through the data acquisition and database management, along with its machine learning models and a clean user interface, it can show the availability and predicted condition of the induction motor. Some disruptions will become a thing of the past, and this can give small and medium enterprises the edge they need to meet the challenges they face today and tomorrow. Furthermore, with its ability to also simulate the motor, it can accurately give laboratory data for students that need to work remotely. The transition to digital futures and what comes next is particularly a capability of what PAL can do.